Hello, my name is Kateryna Kuzmenko. I am PhD candidate at Navier Laboratory at École de Pomparitek under the supervision of Adelaide Feraille and Olivier Baverel. This present study was made in a close collaboration with Nicolas Roussel, entitling Environmental Life Cycle Assessment of 3D Concrete Printing Technology. Concrete is the most used construction material in the world, second most used resource after water. The environmental profile of concrete element is mainly defined by the impact coming from cement production, which is a highly energy-intensive process that additionally emits a large amount of CO2 during limestone decarbonation, making in this way the climate change the main environmental impact category of concrete. Otherwise, the rest of raw constituents needed for the concrete material preparation possess a very low embedded impact, like sand and gravel. And furthermore, the scale of the building element or building system, it has been shown that the traditional construction techniques by casting represent only around 2% of overall environmental impact in climate change category. To sum up, at the scale of material, the main environmental improvement lies in binder with cement substitution. At the scale of a building system or infrastructure, even larger optimization potential lies in a broadly discussed capacity of more precious and rational material deposition offered by digital additive manufacturing, largely known as 3D concrete printing. Thus, when the concrete gets to be deposited with 6-axis industrial robot, the main question from environmental standpoint would be, does this fabrication process remain insignificant from the climate change perspective? And furthermore, does it bring some new pollutants to the system, so-called pollution shift, in some previously neglectable environmental categories? Previously, there has been only one academic work that has been studying the question. However, the mobile robotic construction technologies considered in this study remain very laboratory-like and hardly represents today an industrial setup of printing cell, which leads us to a conclusion of a very poor state of knowledge in the field of environmental profile and performance of 3D concrete printing technology. The methodology of the environmental study is based on life cycle assessment method. The method is briefly consists on tracing all the energy and resources needed for the system functioning from raw material extraction to the end of life. The problematic of the present study addresses mainly the fabrication phase, thus the cradle-to-gate boundaries has been set as the system limit. Therefore, the printing process representing this fabrication phase is set as the process of reference, and the diagram hereby depicts all the processes considered within. Basically, we can see two main flows entering the process of reference, the material footprint and the footprint of robotic printing cell. As today, the general tendency in the practice goes to the material reduction in the printed element. It is not exactly the footprint of material that we are going to be interested in here, but rather the compromise it will make with the impact coming from robotic construction technologies. In order to evaluate this compromise, the functional unit needs to be defined. Thus, in order to ensure the universal approach of the environmental study, the functional unit was set to the elementary brick of any object produced with the extrusion-based additive manufacturing. It has one printed filament with a length L, section A, and overall volume of 1 cubic meter. Going back to the life cycle model, now with the given functional unit, we are going to be able to quantify all the incoming flows needed for its production. Again, we've got three of them. The material footprint that will represent that will be around 300 and 600 kilograms CO2 equivalent per cubic meter. The footprint of robotic printing cell that needs to be studied and characterized, and the impact related to the operational energy. The operational power for the present study was set to 55 kilowatts. This number comes from our industrial partner, X3 company, and represents the theoretical sizing value of power consumption for printing cell, including additional safety margins. The case study for the characterization of robotic printing cell impact is based on X3 layout, which is composed of articulated robot ABB carrying the printing head developed in-house, supplied from concrete preparation unit, and commanded by the computer workstation. Again, the impact coming from robotic construction processes will be defined by two factors. First, the impact related to the production of all the cell's components, and second, the impact related to the operational energy, which is entirely defined by the type of electricity generation. In order to evaluate the footprint of robotic printing cell, a detailed life cycle model was assembled and its outlay to the printing process is extensively studied. So here we've got the first results extracted from my present PhD work, concluded to the hourly contribution related to the production of the cells to be around 2.2 kilograms CO2 equivalent per hour that the system will collect while printing. At this point, this number can be considered as negligible comparing to the impact coming from material. Furthermore, the impact of operational energy, as has been mentioned before, would be entirely defined by the type of electricity generation, which varies from one country to another. In the present study, we have been considering the world average electricity mix, which represent around 0.75 kilograms CO2 equivalent per kilowatt hour. And according to our first measurements, we choose an approximate value of consumption power of printing cell of 25 kilowatt. These values are still need to be validated with detailed measurements currently guided by our team. Finally, the material footprint is not at all the focus of the present study, but its approximate impact is important in order to estimate the contribution coming from a robotic printing cell. Therefore, a generic mix design of printable concrete has been formulated at Navier Laboratory, and its impact in climate change category would represent around 466 kilograms CO2 equivalent per cubic meter. To sum up, the environmental impact of any 3D concrete printed element will be defined by these three components: the material footprint, the robotic footprint, and the impact related to the operational energy of 3D printing process. So here we've got the first results of the case study of one printed filament with a total volume of 1 cubic meter deposited with a speed of 200 millimeters per second with a printing section of 1 square centimeter. Therefore, in the category of the climate change, the total impact of 1 printed cubic meter will represent 750 kilograms CO2 equivalent. And the contribution coming from robotic printing processes in here will be around 35% of the overall impact. Regarding the other indicators, we can constate an occurring of the significant impact transfer and pollution shift caused by robotic construction processes. However, these data are still need to be normalized to the global industrial context. In other terms, regarding, for example, the indicator of agricultural land occupation, where the robotic construction processes represent around 98%, it could simply mean that the contribution of the concrete is so low that the one of robot turns out to be tenfold, when in absolute it's still very, very small and remains neglectable in global industrial framework. In closing, let's take a closer look on the overall system sensitivity, in particular the robot concrete partitioning of the impact in function of the printing section. For this part, the printing section of 0.2 square centimeters till 200 square centimeters were considered. And the present figure depicts a progressive decrease of the overall impact and particularly the contribution coming from the robotic printing cell in function of the printing section, which can be explained by a simple fact that when the printing section of 1 square centimeter is considered, a distance of 10 kilometers has to be traveled by 5 tons robotic arm in order to deposit 1 cubic meter of mortar. This distance increases till 50 kilometers when the printing section of 0.2 square centimeters is considered, and this distance decreases till 50 meters when the printing section of 200 centimeters is considered. Which brings us to a conclusion that independently of technological setup of printing cell, the contribution of printing process to the overall environmental impact of the element will be largely dominated by the mass of the printing device and the distance it travels in order to deposit a certain amount of material. At this point, the overall conclusion can be drawn that depending on the printing process parameters, the printing process may contribute significantly to the overall environmental impact of 3D concrete printed element. The importance of operational power contribution relates to the distance traveled by the printing device and therefore is defined by both the section of the filament and the local type of electricity mix. The detailed measurement of power consumption remains to be accomplished in order to validate the present hypothesis. Furthermore, a synthesis has to be done at the scale of a building system and compared to its conventional analogues in order to ponder a supreme question of the overall environmental performance of 3D concrete printing technology and 3D concrete printed elements over their conventional analogues. Thank you for your attention.